So yesterday we just went over the administrative stuff, and I gave you a little bit of an introduction to number theory and what the true definition of a number was and how it works. I want to continue with that today into our basic operations. We talked yesterday about the count and the name and those two parts of the number and how they look differently in different forms of a number, from a whole number to a fraction to a decimal and into algebraic numbers. You might be wondering, well, how does that really apply to the numbers I use every day? Well, another very simple concept, but also misunderstood, like the idea of a number, is the concept of place value. Now, I know you're all familiar with place value, so I'm not going to insult you by going over this in detail. But there are some pieces of it that's important to go over to make sure you see how it fits into everything else. So our place value, starting at the decimal point or the end of the number and working backwards, we have ones, tens, and hundreds. And those are the only three place values, and they repeat over and over again. Ones, tens, and hundreds. And ones, tens, and hundreds again. And then, of course, these first three here are just what's called the base group. The next three are the thousands group. And the next three, millions group. And of course, when you name a place value, you name its place value and its group. So this would be just the tens group. This is the 10,000s and the 10 millions, so on. Like I said, I'm not going to insult you by going over a lot about how do you pronounce a number or anything like that. But knowing these place values, making sure you have them down is very important for a lot of things in math. For example, one of them, wrong mouse, that's why it wasn't moving what I wanted it to move. One of them is a problem that looks something like this. If I ask you to round 3,782 the nearest 100. Well, we all know how to do that rounding, but I want to show you what it actually really means, what's really happening there. When we say round 3,782 to the nearest 100, what it's really saying is, imagine that we have a number line, and it's numbered in hundreds. So 3,600, 3,700, 800, 900, and so on. What it's saying is, if we put 3,782 on that number line, physically, which of those hundreds is it closest to? Well, it's closest to the 3,800, so that would round to 3,800. Now, obviously, you don't want to draw out a number line every time you round, so we've learned shortcuts. First, the nearest 100, you identify the hundreds place. That's the 7. That's the digit in the hundreds place. But what that's telling us here, that 7, finding that 7, is that this number is between 3,700 and 3,800 on the number line. And so to figure out which of those two it's closest to, we look at the next digit. If that next digit is a 1, 2, 3, or 4, we know it's closer to the smaller one. If it's a 6, 7, 8, or 9, we know it's closer to the larger one. The difficulty comes if it's a 5. If it's a 5, it's right in the middle. Now, for this one, of course, that next digit's an 8, so we round it up. But what if it were 3,752? We find the hundreds digit, which is the 7, and that next digit is a 5. 5 is in the middle. Well, we've always been told to do what with those? Round them
Up.
up, yes. Now, if you asked your teacher why, you might have got an answer like, well, we just do, or it's a convention. We've just accepted that that's what we do. Well, and that's partially true, but there's more to it. This isn't just 3,750, it's 3,752. If I put that on the number line, it's right here. It is actually slightly closer to the next one up. So when that next digit is a 5, we round it up because usually there is more after the 5 that makes us closer to the higher number. Now in this class, if that next digit is a 5, we are going to always round up. But since you guys are in the machining trades and the mechanical trades, you may encounter times when somebody might round it down when that next digit is a 5. You don't need to put this in your notes because you're not going to be tested or quizzed on it. But it is a common thing in mechanical engineering and mechanical design to do something called rounding to the evens. And it only applies when that next digit's a 5 and there's nothing else after it. Like if we have 275, 425, 355, and 185. If I wanted to round all three of those to the nearest 10, well, on all three of those, I identify my tens digit, and that next digit is a 5. Again, for this class, we're always going to round it up when that next digit's a 5. But in mechanical design and machining, you will sometimes run into places where people round it down. And the reason for that is for tolerance buildup or error buildup. If we rounded all of these up, and these were all dimensions that were one after another on a part, well, if we rounded all of them up, by the time we got to the end of the part, we would be way bigger than we needed to be because those round-offs would add up on us. They would build up on us. So in rounding to the even, what we do is we start just like we normally would to round. Here's the tens digit. That's a 7. We look at the next digit and see that it's a 5. Well, when we see that that digit is a 5, we look back at that first digit in the tens place. Is the 7 an even number? No, it's odd. So we are going to round it up to make it even. Over here, 425, that's a 2 in the tens place. The next digit's a 5. When we look back at the digit in our tens place, is the 2 even? Yes. So we leave it at 2. Over here, in the tens place is a 5. The next digit is a 5. So we look back, is that 5 even?
No.
No, so we round that up to an even digit. And in our last one, this is an 8 in the tens place. The next digit's a 5. So we look back to the tens place. Is that even? Yes, 8 is even, so we leave it as an 8. So this mechanism, rounding to the evens, allows us to, when that next digit's a 5, we round some of them down and some of them up, and we round some of them down, so that error buildup doesn't build up on us and cause mistakes. Now, like I said, for this class, we're always going to round like this. If that next digit's a 5, we round up. Rounding to the evens only applies if that next digit's a 5 and there's no other digits after it. And like I said, I'm only showing that to you. I'll never quiz you or test you on it. I'm showing it to you so that if you run into a mechanical engineer or mechanical designer somewhere that rounds like that, you don't think they made a mistake. You understand that there is a way of rounding like that. Now, the other big application of this place value I want to talk about is how it really defines a number. What we're used to seeing is not really a full number. We see that as 374. Well, that's not really the whole story. That's actually just an abbreviation. The full form of that would look like this. 300s and 7 tens and 4 ones. That is the full form of that number. And when we write it out like that, we can see, each digit has a count and a name. This is not just a 7, it's 7 tens. So if I go to do an operation with it, let's try to add 424 to it. So I'm going to write that out in its full form as well. 400s, 2 tens, and 4 ones. From yesterday, those of you that weren't able to make it in yesterday, hopefully you were able to see the video. We talked about when we add or subtract, we can only combine things that have the same name. That means that these 2 tens here can only be, these 7 tens can only be combined with these 2 tens here. That's why we've been told our whole life to make sure you line up the columns when you add or subtract, because we can only add the ones to the ones and the tens to the tens and the hundreds to the hundreds. Once we have those lined up, we can go ahead and just add. 300s and 400s make 700s. 7 tens and 2 tens make 9 tens. And 4 ones and 4 ones make 8 ones. So there we have it, 708. Now, if you were watching closely, you may have caught that I did something a little strange there. Did you see what it was? I added left to right. Typically, we start at the end of the number and we add right to left. We do that in case we have to do what?
Carry over.
Carry over, good. In a number like 468 plus 279, we start on the right and work our way back to the left in case we run into this. 8 plus 9 is 17. But we can't have 2 digits there, so we keep the 7 and we carry the 1. 1 and 6 is 7, plus 7 is 14. So again, we can't have 2 digits, so we'll keep the 4 and we carry the 1. 1 and 4 is 5, plus 2 is 7, so we get 747. Now, this process of carrying is relatively new. Now, in math, by new, I mean in the last couple hundred years. But before carrying was common, another way this problem would have been added might have looked something like this. 4 plus 2 is 6. 6 plus 7 is 13. So 3 drop the 1. 8 and 9 is 17, so 7 drop the 1. We got 6 and 1 is 7, 3 and 1 is 4, and 7. Now you notice we get the same answer. It's a little bit longer, takes a little bit more space, but we still get to the same answer. Now, my point in showing you this is not to try to change the way you add numbers. It's just we've been taught, our whole lives we've been taught there's only one correct way to do math. That's not really true. There's only one correct answer, but there are several ways you can get to that answer. I can show you 2 or 3 more ways of adding numbers that will always give us the same answer, but look very different. I'm not going to do it because I don't want to confuse you. But if you have a way of doing things that's different from what I show you, please don't feel you're doing it wrong or don't feel you have to change it to do it my way. If you're not sure that the way you're doing is correct, talk to me and show me and I'll look at it and I'll let you know if that's something that will work every time. The important thing in math for me is not that you do things the way I do, but that you do things in a way that's going to give you a reliable result, and it's a way that you understand. When it comes to math, we've been taught all these shortcuts like this to the point where the actual process doesn't even appear anymore, and it doesn't really make sense with our base concepts anymore. So you're trying to memorize those shortcuts, and that's where you start to lose track of math and it gets confusing. Now, the realist in me says we have the calculators, and I know you're going to use them. So in a problem like this, 468 plus 279, I realize when there's 3 digits involved, not many of you are going to actually take the time to do that out by hand, and I don't blame you. But before you punch it in the calculator, I would hope that you would at least do this little bit of a thought process or something similar to it. 468, well, that's about 500. 279, well, that's about 300. 500s and 300s, well, 5 plus 3 is 8, and we keep the name of hundreds. We're expecting an answer around 800. So when the calculator spits out 747, that makes sense to us. Because it's very common to do something like this. 468 plus 279. Oh, 497. Well, what went wrong there? You see, one of my keys didn't register when I pressed it. Or we can have something like 468 plus 279. Well, 4,900 is not correct either. You can see I accidentally hit an extra key when I was typing that one in. So having that little bit of an estimate before you punch it in the calculator helps catch those mistakes like that. It doesn't catch all of them, but it catches the worst ones like that. For subtraction, I think you guys get the point that we have to line up the columns, so I'm not going to write them out in full form. But let's take a look at something like 758 minus 235. Again, just like addition, we can only combine things that have the same name. So I can only combine ones with ones, tens with tens, and hundreds with hundreds. Once they're lined up, we go ahead and subtract. 7 minus 2 is 5. 5 minus 3 is 2. 8 minus 5 is 3. So we get 523. Now again, you'll notice I went left to right. We're used to going the other direction. In subtraction, it's in case we have to do what?
Borrow.
Borrow. Good. We have a problem like this. 852 minus 379. We start on the right and work our way back to the left because we run into this. 2 minus 9 can't be done. So we borrow from the 5. That's a 4. This becomes a 12. 12 minus 9 is 3. 4 minus 7 can't be done. So we borrow from the 8. That's a 7 now, and this is a 14. 14 minus 7 is 7, and 7 minus 3 is 4, getting 473. Now again, that process of borrowing is not the only way that subtraction can be done. A different way that was done would look like this. 8 minus 3 is 5. 5 minus 7 can't be done, so we actually borrow from the 5 down here to make it a 4. This is a 15. 15 minus 7 is 8. 2 minus 9 can't be done, so we borrow from the 7, or 8, make it a 7. This is now a 12. And 12 minus 9 is 3. Notice we get the same answer. Again, this probably takes up a little more space, but really what we're borrowing from is the result at the bottom of the column, not the number at the top. Again, my point is that there are several different ways that you can approach math. Let's look at multiplication. Keep it fairly simple, something like 32 times 21. This one I am going to write out in long form, in full form. So 3 tens and 2 ones, and 2 tens and 1 1. Now, yesterday we talked about when we multiply or divide, we do not need the same name. So what that means is these 3 tens not only can be combined with these 2 tens, but they can be combined with the ones and any other digit as well. In fact, every digit in the top number can be combined with every digit in the bottom number. And that's all long multiplication is an organized way of making sure that happens, that every digit in the bottom number gets combined with every digit in the top number. The difference in process really is just where we start and how we organize it. For most of us, what we were taught is you start with the bottom number and you start with the last digit of that bottom number. So the 1 1 in this case. Then you combine it with the digits in the top number, starting with the last digit in the top number. So let's combine them. 1, 1 times 2 ones. Well, combining counts. 1 times 2 is 2. Combining names, 1s times 1s is 1s. Moving over to the next digit in the top number. 1, 1 times 3 tens. Well, 1 times 3 is 3. 1s times 10s is 10s. Now we've combined it with every digit in the top number. We move over to the next digit on bottom. We've been taught that when we do that, down here we either have to put in a 0 or leave a space. The reason for that is right here. This is 2 tens times 2 ones. 2 times 2 is 4. Tens times ones is tens. We had to put that 0 in there just to keep our place values lined up. And then we have the 2 tens times 3 tens. 2 times 3 is 6. Tens times tens is hundreds. And then we go ahead and combine. 2 ones and 0 ones is 2 ones. 3 tens and 4 tens is 7 tens. And the 600s. So we get 672. Now again, I realize you have a calculator and you're going to punch that in, and I don't blame you. Again, I use the calculator now too, rather than trying to do that out longhand. But I would hope you'd look at this and say, well, that's about 30. That's about 20. 3 times 2 is 6. When we multiply, we combine names, though, so tens times tens is hundreds. We're expecting something around 600. Now, division, arguably, division is the most difficult of our operations to do by hand. It's also the one that they've done the most to try to abbreviate and shorten and trying to make it easier. And in that process, they've lost sight of what division really is. If we look at, remember we said multiplication and division were closely linked. They're the same operation. One is going forward and one's in reverse. So if you think back to first grade or so, when you started multiplying, 5 times 3, before we memorized our multiplication tables, and we just knew that that had to be 15. The way we figured that out was something like this. 5 plus 5 plus 5 is 15. We did repeated addition. Well, if multiplication is repeated addition, division is repeated subtraction. 24 divided by 8 is telling us to subtract 8 from 24. Subtract 8 from 24, we get 16. We subtract 8 again, we get 8. Subtract 8 again, we get 0. Subtracted 1, 2, 3 eighths. 24 divided by 8 is 3 because you can subtract 8 from 24 3 times before we hit 0. Well, that process of repeated subtraction is fine, except a little tedious if we get into a longer problem. If I have something like 72 divided by 3, let me move this over a little bit. I'm not going to start subtracting 3 from 72. That's going to take a while. But what I can do is this. I can subtract a bundle of 3s. How big of a bundle? Well, I look at my place values. The number I'm dividing, the 72, that first digit is in the tens place. So let's subtract a bundle of 10 3s. 10 times 3 is 30. Well, I can actually subtract that more than once. I can actually subtract that twice, which would be 60. 72 minus 60 leaves us with 12. Well, what I just did there was I subtracted a bundle of 10 3s, and I did it twice. 10 times 2 means I just subtracted that 3 20 times. That's what the 60 did. And then, of course, all that's left is the ones place. 1 times 3 is just 3. I can do that 4 times. 3 times 4 is 12, leaving me with nothing. So I just subtracted that 3 4 more times. So that's 24. 72 divided by 3 is 24, because I can subtract 3 from 72 24 times. But notice I didn't have to do it once at a time. I could do it in those bundles. Our process of long division is just an organized way of doing that subtraction. Let's do 7,854 divided by 21. Well, 21 does not go, well, I'm not going to start subtracting 21 from 7,000. We don't have that kind of free time. So let's do bundles. That first place value there is thousands. 1,000 times 21 is 21,000. Well, that's too big. I can't subtract it. So our next place value would be hundreds. 100 times 21 is 2,100. I can subtract that. In fact, I can subtract it 3 times. 2,100 times 3 is 6,300. So I subtract that 4, 5, 5, and 1. Well, what I subtracted there, I subtracted a bundle of 121s, and I did it 3 times. 100 times 3 is 300. This 6,300 was subtracting 21 300 times. My next place value is the tens. 10 times 21 is 210. I can subtract that from what's left. Looks like 7 times. So 210 times 7 is 1,470. I subtract, I got 4, borrow here, 15, 84 is left. Well, again, what I subtracted was 10 21s, and I did it 7 times. So 10 times 7 is 70. I just subtracted 21 70 more times. Of course, now I'm down to the ones place. 1 times 21 is just 21. 21 times 4 is 84, which gets me to 0. So I just subtracted 21 4 more times. So my result here is 374. Now, I am guessing that most of you are looking at what we did there and thinking, that looks nothing like what we were taught for long division. And it doesn't look much like it, but it's actually exactly what you were taught. Let's take a look. So 7,854 divided by 21. What we were taught was this. You go to the first digit, the 7. Does 21 go into 7? No, so we leave it blank above that. That's exactly what we did right here. The 21,000 was too big, so we went to the next place value. Now we move over to the next place value. There's 78. Does 21 go into 78? It does, and it goes 3 times. 3 times 21 is 63. We subtract to get 15. Well, again, that's exactly what we did over here. We just left off the zeros. Oops, not there. The year would be the 0. So we just didn't put the zeros in. Now over here, we had to bring down the next digit. 21 into 155 goes 7 times. 7 times 21 is 147. Again, that's exactly what we did over here. We just left off those zeros. So we subtract 8 here. Come on. Bring down the 4. 21 goes into 84 4 times. So it is the exact same process. What we were taught is just a shortcut where we leave out all of these steps here. We're actually doing those steps in our mind, but we're leaving them out when we do the process. To me, obviously it looks strange to you right now, but once you get used to it, this longer process makes way more sense because you see why it is that you only have to work with those first couple of digits rather than having to do the whole number. Why is division the only operation that goes left to right instead of right to left? Well, it's because we're subtracting the larger bundles first in order to get to our answer. Now, like I said, long division is one operation that I won't really try to do by hand if I have a calculator available. So I at least hope you look at this and say, well, that's about 8,000. And this is about 20. 8 divided by 2 is 4. Thousands divided by tens is hundreds. So we're expecting an answer around 400. So the big moral of the story is make sure before you punch anything in the calculator, you have an idea at least of what you're expecting that answer to be. Okay, so that is our material for today. We do have homework today. For those of you that weren't able to make it yesterday, there was no homework yesterday. For today we have homework. We have the 2 books. I usually just refer to it as the little book. That is your small practical problems in mathematics for industrial technology book. And it is units 1, 2, 3, and 4. I'm going to ask you the odd numbered problems. Now, a couple of things here. The odd numbered problems have all the answers in the back of the book. So please check your answers as you're doing them. The last thing I want is for you to do a dozen problems and then realize you've done them all wrong because you really haven't learned. The only thing you've learned is maybe a bad habit on doing it incorrectly. So please check your answers as you go. Make sure you're doing them correctly. If there's any that you can't figure out how to get to the answer they have, that's where we start class tomorrow, is by answering those questions and going over those. Excuse me. Also, I realize that, especially here at the beginning of the semester, some of these problems are pretty easy. So as you start the assignment, if those first few problems are way too easy, feel free to skip ahead to some of the more difficult problems. Just make sure I'm not gonna, like I said, I'm not gonna collect your homework and grade it in detail. We're just, as long as you're using your homework time, you're gonna get credit for the homework. I just want to make sure you do some of the more difficult problems at the end of the end of each section, so that you're familiar with them. Because it's real easy to look at these and say, "Oh, that's easy," and not do anything, and then realize later that, well, it looked easy, but you're not really sure how to do it. So make sure you're doing at least a few of the more difficult problems at the end of the assignment. But if you're comfortable taking a quiz, I am not going to criticize you for not doing every problem on the homework. Now, the other side of that is if you are struggling with the material, that's why you do have this size of a homework assignment, so you do have plenty of problems to practice on and get comfortable doing it. So, like I said, for those of you that weren't here yesterday, I do not collect the homework and grade it. Your homework grade is just on using your class time wisely. We only have like 3.5 minutes today, so I'm not going to make you stick around and start your homework today, but usually we'll have about 10 minutes or so to start the homework assignment. So for now, that's your homework. For those of you that weren't here yesterday, is there anybody that has not accessed Blackboard yet? You guys are in Blackboard. That's good. Make sure I'm double checking that. In Blackboard, as I mentioned yesterday, it is the course information section. And there should be a folder at the bottom of the page of that course information section. There should be a week 1 folder. If you open that folder, it'll have all the recordings and stuff from yesterday, so you can go back and view those recordings and catch up. Anybody have any questions? Okay, I will let you guys out of here for the day. We'll see you all tomorrow. For those of you that are logging in for the next class, I am going to log out quickly and then be right back so that I can separate the recordings.